So we're going to be talking about Lagrange multipliers. This sounds a little bit scarier than it actually is. Essentially, when we were talking about our maximization and minimization problems on Wednesday, this was all about, we've got some surface, say some function of multiple variables, and we want to find critical points, and we want to find where this function is, say, maximized or where it's minimized. And there are lots of different contexts where you might want to maximize something. We talked about, say, an agricultural example where you can put in different amounts of nitrogen, different amounts of phosphorus, and this will affect your crop yield. Okay, so you want to maximize your crop yield. You can put in any amount of nitrogen, any amount of phosphorus, and therefore that's going to ultimately affect your output. So we can do these kinds of optimization problems where you have a wide range of parameters you can put in, and you could think about this as being the entire domain of a function. Okay. This lecture here today is all about constrained optimization. You can think of that as essentially being, okay, rather than having the entire domain of input values, so you can put any amount of nitrogen in, any amount of phosphorus in, you have some constraint which is defined by a curve. Okay, so perhaps nitrogen, and you have, say, a fixed budget, and nitrogen and phosphorus cost a certain amount each. You might say, well, actually, the amount of nitrogen you put in, if you put more of that in, you have to put less phosphorus in, or vice versa. Okay, so there might be some trade-offs involved in terms of what you can put into the system, and those trade-offs can define, say, a line or a curve through your space, and that will limit the amount of the function, or rather the input values that you put into your function. Okay, so what that looks like then is if you've got a surface defined by level curves like this on the bottom left, rather than putting in any xy value, you're constrained to these values. G of xy is equal to k. So values on this blue curve here. Get my pen to work. There we go. So it says you can only put in values of x and y that sit on that curve. And therefore, although you've got this function that can take any xy values here in this quadrant, saying we're only going to limit ourselves to those, and therefore can we find the maximum or minima that lies on that curve. And intuitively, if we think of our level curves, as you cross a level curve, you can't be a maximum or a minimum. Okay, so if we look at this point here, as you cross the level curve below this value, f is less than 7, and above this level curve, f is greater than 7. Okay, so that means that we can't ever have a maximum or a minimum when we're crossing a level curve. Okay, the only points that we can are when we are tangent to a level curve. So when our constraint curve is tangent to a level curve of our function. What that means then is that we know our gradient of our function, our grad of f, is always perpendicular at right angles to our level curve. And that means as well that our gradient of our constraint curve is going to be parallel or anti-parallel to our gradient for our function. So grad of f is going to be parallel or anti-parallel to grad of g. In other words, this is just because your constraint curve is tangent to your level curves, and we know that our gradient function is perpendicular to our level curves. So that means that the gradient for our f and our gradient for our g are going to be parallel or anti-parallel. So it can be anti-parallel because there's no reason why they necessarily have to be pointing in the same direction, but they could be pointing in the same direction. This all leads us then to a method of Lagrange multipliers. So if we've got a diagram like this, we could just, pick out where is the level curve tangent to our constraint curve. That's fine. If you don't have that, or in many dimensions, say you can't visualize it, we can use the method of Lagrange multipliers, which essentially says that if we've got some function f and we've got some constraint condition g, then our maximum or minimum value of our function subject to that constraint occurs when our gradient grad f at that point p is equal to a multiplier lambda, which is called our Lagrange multiplier, times by the grad of g at p. And all that's saying is that this grad of G here, that slightly reddish brownish line there, that vector, is some scalar multiple of our gradient of f at that point, okay? So it's just stretching it and maybe flipping it around. That's fine. So lambda could be positive or negative. And that's all it is. So really that's just a set of equations, a system of equations that we need to solve, okay? So we can work out our grad of f and our grad of g, and those are just composed of our partial differentials. Okay, so we know that grad of f with respect to x, the partial of f with respect to x is going to be lambda times by the partial of g with respect to x. Likewise, we know that f sub y, our partial of f with respect to y, is going to be lambda times by partial of g with respect to y. And then we have this third condition here, our constraint condition g is equal to some k. We often would write this as g minus k is equal to 0, okay, or k would just be equal to 0. Okay, so this allows us to find potential locations for our maxima and minima. And we can do this, like I said, just looking at level curves. For example, in this diagram here, this point P is a minimum, it turns out, for this green constraint curve. So say if we start down here, we can think of this as maybe walking down a hill, and these are contours on a hill showing the height. And what is the lowest height that you reach whilst you're taking that path? And it turns out here it would say be 8 meters, okay? So you can imagine these as following a path, if that helps to visualize it, that you're going out for a hike and you're following a path on some hillside. What's the maximum and minimum height that you reach? Okay. If we just have a set of equations like this, we've got some surface here, P of xy, and then we've got this constraint here. How do we solve this? Well, we just set up our system of equations by looking at the partials. So we have the partial of P with respect to x is equal to lambda times the partial of G with respect to x. Same for y, and then our constraint curve. And then we've got 3 unknowns. We've got our x and our y, which gives us the point at which our maximum or minimum occurs. And then we've got our lambda, which tells us what the scalar multiple is of our gradients, okay? So we can use these to solve for x and y. And that is essentially it. Does anyone have any questions about any of the material from the pre-recorded lecture? Nope. Oh, yes. Sorry, say a bit louder, please. These ones? This was just substituting in these points here into our function f. So if we take these points, x is 3 over 2, and y is either plus square root of 3 over 8 or minus square root of 3 over 8, and then substitute it back into this function here, it will give our function values here. Okay? Any other questions? Yes? How did you know this minimum and this maximum? That's a good question. So here we've got a diagram, so we can work it out. Ignore the diagram for a second. Suppose we don't have that. Suppose all we've done is we've worked out from the above. So from this slide here, we've worked out our possible x values and our y values from this calculation up here. So what's circled in green. So that gives us 4 points. And those 4 points tell me that these are minima or maxima. Okay, these are the only places where minima or maxima can be, because these are where our gradients of f are parallel or anti-parallel to our gradients of g. Okay, then all we do is we plug each of these values into the function. So this value here, the x and y values of 1 and minus 1, into this function up here. And then that will give me a number out. So this gives me a 5, this one here gives me a 1, and then we have something that's about 2.69 and something that's about 3.31. Okay, so because I know that these are all the minima and all the maxima for our function on that constrained curve, well, I just need to pick out the biggest one. That's the maximum. 5 is the largest one, so that's the maximum. And that's an absolute maximum. 1 is the smallest one, so that's an absolute minimum. The 2.69 Well, this is a little bit trickier here because we can't tell whether that is a minimum or maxima just by looking at its value, right? We can tell that 5 is the largest value, so it has to be a maximum. 1 is the lowest value, so it has to be a minimum. The 2.69, 3.31, we would have to either draw this or do a little bit more analysis to work this out. If you have a curve like this, we can plot where these values are. So this is an absolute minimum, and this is the absolute maximum. So we knew those just by plugging the values into the function or by looking at where these points are on these level curves. So this one here was on the level curve 1, and this one up here is a bit hard to see, but that's a 5 there, okay? So we can look at our level curves to see what those values are. These ones here, we can also tell by where they approach. So if you just had the diagram and you didn't have what the functions were, you could tell whether these are local minima or local maxima on the right-hand side by looking at how your constraint curve approaches the level curves, okay? So imagine you are walking, imagine this is a hillside and you're taking a big loop around this. You wanna know, are you going downhill or uphill, okay? So here, because you're in this direction, as I'm drawing this arrow here, if you're walking this way, you're crossing level curves going from higher values to lower values. So you can think of that as walking downhill, right? And here, you reach a tangent to the curve, to the level curves, and then you start going uphill again, up here. So you've gone on that curve, you've gone downhill, you've reached a point, and then you're going uphill, which means that must be a local minimum. So if you look at how you approach those level curves and where the tangent is, and that will tell you whether you're at a minimum or a maxima. And if you contrast it with this case up here, where we've got a local maximum, well, here, we already know that we're walking uphill, right? So you're crossing the level curves from below. So the function value is increasing. You reach a particular level here, which was, what was it, 3.31. And then on this side, you're going down again. So you're crossing down across the level curves and the function value is decreasing. So you've gone from below, you've gone up, hit a point, and then you've gone back down again. So you know that it's a maximum. Okay, it's a good question. Any other questions about this? Okay, let's solve some problems. Okay, so we have a diagram very much like the one that we just talked about. What I want you guys to do is identify where the minima and the maxima are on this curve. What I'll do is I'll zoom in a little bit, so it's a little bit larger in case you don't have it written down. Identify approximately where the maxima and minima are on this curve, and then whether they are local minima, local maxima, absolute minima, or absolute maxima. Okay, and I'll walk around and answer any questions. Okay, while a few people are still working on that, can anyone tell me how many they think there should be? Yeah, 3. I'm going to go around and see what other people think. 4. Anyone else? 5. 3, 4, 5. I'm going to say that at least 2 of you are wrong, but it's okay. Anyone else? Any other guesses? Okay, so we've got possibly 3, possibly 4, possibly 5. One of you is right. Okay, let's work through this. So what I'm going to do is start in this top right quadrant here, and then just work our way around. Okay, so what I'm going to do is I'm going to draw, hopefully this will work. I'm going to draw on this, and I want you guys to tell me roughly when I should stop. I've not tried this before, so it might not work very well. Tell me when you think that there's a minimum or a maximum. Okay, it's about there. And why? Because it's tangent. So it looks like just about there, it's tangent. We can also see that up on this side here, we're tending to, like, we're increasing towards that level curve. And then on this side, we're going away from it. So that tells me that we must have changed direction at that point. Okay, so here we've got some candidate, and this is, what's the value there? I can't even make that out. Is that 8, I think? Yeah. 8. Okay, so we've got a value of 8. Let's leave that there for now. Let's carry on. Well, what can we say about it already, actually? We don't know if this is an absolute or a local maximum or minimum, but do we know whether it's a maximum or a minimum? Yeah, what is it? Okay, so we know that it's at least a maximum. So I'm just going to put max in there for now. Okay, let's carry on onto this quadrant over here. So again, I'll do the same thing. You probably can't even see that. Let me go into a different color. Is that any better? Kind of. I've obviously got terrible colors on here. Okay, again, tell me when you think. Stop. Okay. There? Can you change your answer? I want to go to 4. You want to go to 4? Okay. So what's this one then? Is this a local minima, a local maxima? I heard some murmurings, a bit louder. Minimum, okay. So we know it's a minimum because you're approaching from above, and then we're going to be changing direction on this side and going away from it, so it's a minimum. Okay, so this value here was, I think, 4, by the looks of it. Okay, I'll speed it up a little bit. I've got a better color. Let's see if this one's any better. Okay, going away from it. Again, shout. Stop. Okay, you guys have got this. Is this a minimum or a maximum? Maximum of, say, about 6, I think. And then if I carry on, I'm just going to keep this color here. Tell me when. Okay, minimum or maxima? A value of 1. And then if I carry on, we're back to where we started. Okay, so there's 4. So that's all we need to do. Just follow a little trajectory going around to see where you get to being a tangent to the curve. So we've got these values here. We've got 1, 4, 6, and 8. So we know that this one up here is an absolute or global maximum. This one here is an absolute or global minimum. And then these two here, this one's a local maximum, and this one's a local minimum. Do you notice anything about the ordering of these things? Go for it. Max, min, max, min. Yeah. So you're always going to go max, min, or min, max, right? Because you can't have 2 maxima next to each other. If you had 2 maxima next to each other, then one of them can't be a maximum, right? Because you have to go down before you have to go up, in which case there'll be a minimum between them, okay? So always remember, if you were doing a diagram like this and you had 2 maxima next to each other, you've made a mistake, right? It'll also tell you that you can't have, say, on a curve like this, you wouldn't be able to have 3 or 5. Okay? You wouldn't be able to have an odd number, because if you wouldn't be able to go from a maximum to a minima to a maxima to a maxima, right? If you're following a closed curve around like this, okay? Good, well done, everyone. So seems like you guys have got the hang of it when we are doing things graphically. Let's have a go at method of Lagrange multipliers, okay? So now we don't have a graph here. We've got some function f of xy is equal to xy, and we've got a constraint x plus y is equal to 4. Okay, so what I'm going to do is I'm going to write this here as g of xy is equal to x plus y minus 4. And we want to set that equal to 0. That's a slight convention thing. You could leave it as g of xy is equal to, well, actually you need to take the derivative of it. So it's best to put it in this form here. So you want to do our method of Lagrange multipliers. And all that means is we need that grad of f is equal to some constant lambda, non-zero constant that is, times by grad of g. And that's going to give me 3 equations. Can anyone tell me what the first equation is? Well, it's going to give me 2 equations, actually. We've got this third equation here is just our constraints. This is just our g of xy is equal to 0, or x plus y is equal to 4. So what 2 equations do we get from this here that we need to solve? Partial of f with respect to x is equal to lambda times by partial of g with respect to x, okay? And then here, what's the other equation that we're going to get? partial of f with respect to y is equal to lambda. Again, this is the same lambda here, times by partial of g with respect to y. Okay, so you know how to work out partials. You know how to solve systems of equations. Have a go at seeing if you can find out what the x and y values are here. Once you find out what the x and y values are, substitute them back into your function f, and then try and work out if it's a maximum or a minimum. And you can do that just by looking at considering a different value of your function, okay? Okay, can anyone tell me what this first equation over here is going to be? So you do our partial of f with respect to x is what? Y is equal to lambda times partial of g with respect to x, which is so just y is equal to lambda. Okay, so we already know that y is equal to lambda. How about second? X is equal to lambda. Okay, great. And then we've got this constraint curve on the right-hand side. So what we need to do now is we need to substitute these values into here. Okay, so if we substitute y is equal to lambda and x is equal to lambda, we're going to get lambda plus lambda is equal to 4. In other words, lambda is going to equal 2. And because x is equal to lambda and y is equal to lambda, that means that we have our maximum or minima is equal to 2, 2. Now all we need to do is substitute this back into our function f. So we substitute 2, 2 back into this function up here, xy, and we get f of 2, 2 is equals 4. Okay, so we've got this far. How do we know whether this is a maximum or a minimum? Well, recall that on this constraint curve, and when we're passing through this function f, the method of Lagrange multipliers is going to give us every possible maximum or minimum. Okay, the fact that we've only got one point here means that it either has to be a maximum or it has to be a minimum. Okay, if we'd had two, then we'd know that one was a maximum, one was a minimum. Okay, and we'd have to do a bit more analysis to figure out which is which. Because there's only one here, we know that this has to be either an absolute maximum or an absolute minimum. Okay, because it's the only one. So that means that we could just look at another function, a value of our function that is on this constraint curve. So substitute in some other values of x and y, where x plus y is equal to 4, and see what the value is. So for example, if we look at f of, say, 0, 4, so x is 0, y is equal to 4, then our x plus y is still equal to 4. What's the value of that? Well, we can have 0 times by 4, which is 0. And this is less than our f of 2, 2. Therefore, that tells me that xy 2, 2, xy at point 2, 2 is what? A maximum. In fact, it's an absolute maximum. Okay? So it's nice and straightforward. So if we visualize what's going on there, all these level curves here, that's our function f of xy is equal to xy. And then our constraint curve, x plus y is equal to 4, is actually just a straight line, given by this green line here. And we can see that it's only tangent to these level curves at this one point here. And that point there is when f of xy is equal to 4. So it's on that level curve 4. So we can see that this is a max at 2, 2. We see it's at 2, 2 because we can check off these values here. And it has a value of 4. That's it. Okay, any questions about that example? Nope. Okay. Let's do something a little bit more complicated. What we have here is we've got a surface. note that we've now got 3 variables, but just because we've got 3 variables, as with many other things in this course, the difficult step is going from 1 to 2, and going from 2 to 3 is basically just an extension of what we've already done. We've got a point on this surface, and this surface looks like this in the first octant, so when x, y, and z are all positive. And what we want to do is minimize the distance to the origin. So we want to find the point P somewhere on this surface. Let's call it there, P, x, y, z. It looks like it's going to be somewhere around there, right? We want to find the point that is closest between that surface and the origin. So how do we do this? Well, first of all, this is our constraint now, because we need it to lie somewhere on this surface. So now our g of x, y, z is going to be equal to just x squared, y squared, z minus 4. Okay, and our constraint is going to be equal to 0. Question then, what are we minimizing? Well, we're minimizing the distance function, okay? So what's the distance function in R3? We minimize the distance between this point x, y, z and the origin. So what's that going to be? How do we work out a distance in R3 between 2 points? Yeah, so we're doing square root of difference in the x parts, the y plus square root of the difference in the y parts all squared. I don't think I said the first one squared. And then plus the difference in the z components squared. Okay, here, because we've got 0, 0, 0, our origin, it's actually just going to be square root of x squared plus y squared plus z squared. So that's the function that we want to minimize. So this is like our f of x, y in the previous slide, but now we're going to have an f of x, y, z. In fact, this is equivalent to minimizing I'm going to call it f of x, y, z is equal to x squared plus y squared plus z squared. Why do we do that? Well, dealing with square roots can be a bit of a pain sometimes. We know that if you minimize the distance, you're also going to be minimizing the square of the distance. Okay, all you've done is you've squared it. So if we minimize this function here, we're also going to be minimizing this function here. Okay, so we have our function, our distance function, we have our constraint, our g of x, y, z. So all we need to do now is work out our Lagrange multipliers. This is exactly the same as before, so method of Lagrange multipliers. We can have grad of f is going to equal lambda times grad of g. So now we're going to have 3 different equations. I'm going to step through this one with you guys because it gets a little bit complicated. So we're going to have f sub x is equal to lambda times g sub x. F sub y is equal to lambda times by g sub y. And f sub z is equal to lambda times g sub z. And then we've also got our constraint x squared, y squared, z is equal to 4. Okay. So now we've got 4 variables, 4 unknowns, x, y, z, and lambda, and we've got 4 equations. Okay, we need to solve these. So the first thing we need to do is work out our partials. So partial of f with respect to x. Remember, this is our f up here. So partial of f with respect to x is what? (2x), yeah, is equal to lambda times our partial of g with respect to x. What's that going to be? This is our g up here. Yep. So we have a lambda. I'm actually going to bring the 2 out the front, just make it a little bit neater. 2 times by lambda times by x, y squared, z. And if I just fill in the other ones, we have 2y here, because it's basically the same thing, times by slightly different here, 2 lambda x, y squared, z. No, sorry, x squared y z, that should be. X squared y z. And then here we're going to have a our partial with respect to z is going to be 2z is equal to lambda x squared y squared. Okay, so these look quite nasty to work with, but actually they're not that bad. So let's call this equation 1, this equation 2, this equation 3. We'll call this one 4 as well. Okay, so there is no hard and fast rule as to how you solve these. What you need to do is you need to do some algebraic manipulation to try and eliminate things, okay? So what we can notice here is that these right-hand sides are fairly similar, okay? So we've got a 2 lambda xy squared z. In this first case, a 2 lambda x squared yz, and then a lambda x squared y squared. Okay, so they're fairly similar, which means that we could do a bit of multiplication to end up with the same thing on the right-hand side, and then we can equate these. Okay, so in the first case, I'm just going to multiply this first equation here by x over 2. The reason the over 2 is just to get rid of the factors of 2 on each side. And this is going to give us x squared on the left-hand side is equal to lambda x squared y squared z. And then we're going to take equation 2. We're going to multiply that by y over 2. Now we're going to have y squared is equal to lambda x squared y squared z. Notice now we've got the same thing. This here is equal to this. So that means we're going to be able to equate these two things. So let's do that step first. So if we equate these two things here, we're going to get x squared is equal to y squared. So all I've done there is I've manipulated the right-hand side of these two equations, 1 and 2, by multiplying the first one by x over 2 and the second one by y over 2. And the reason I chose those values is just to get the right-hand sides equal to each other, and then I can equate them. Okay, so this gives me x squared is equal to y squared. And because we're told in the question that we're in the first octant, that just means that x is greater than 0, y is greater than 0, and z is greater than 0. Okay, so that means that x must equal y, okay, because we can't have negative values. This is because we're in the first octant. Okay, so we have some, we've made a bit of progress with our x and y now. So let's look at our z. So if we take this equation here, equation number 3, and we multiply it by z, we're going to get 2z squared is equal to lambda x squared y squared z, which again, if you notice, this right-hand side here is equal to the right-hand side of these equations. So all we've done is just done some manipulation here where we're going to be able to do, where we're going to be able to equate things. So now let's equate these two things. So we're going to have a y squared is going to equal to z squared. In other words, we can rearrange this that y is equal to root 2 of z, and because we're in the first octant, which means that x, y, and z must all be positive. Is everyone following what I'm doing so far, or is anyone lost and wants me to explain any more steps? No? Okay. Okay, so we have a relationship between x and y and a relationship between y and z. And because x is equal to y, this tells us that x is also equal to root 2z, just because x is equal to y. Okay, so what do we do now? Well, now we can bring in our constraint. So we've used 3 of these 4 equations here, but we've not used this one, number 4 yet. So we've not used our constraint curve at all. So this means we have the constraint x squared, y squared, z is equal to 4. So all we need to do is we need to substitute in our values of x and y that we've already worked out. So we've already worked out y is equal to root 2z and x is equal to root 2z. So we can eliminate both of those. So that gives us root 2z squared. So that's just substituting in for x. Similarly for y, root 2z squared. times by z is going to equal 4. We multiply that all out. We have a root 2 squared times a root 2 squared, which is going to be 2 times by 2, which is 4. You're going to have a z squared times z, which is z to the 5. That's going to equal 4. That tells me then that z to the 5 is equal to 1, or z is equal to 1. Because we know that y and x are both equal to root 2z, we've got a value for z now, so we can just substitute it back into these equations up here. And then we can say xyz is equal to root 2, 1 is closest to the origin. So that's the closest point on this surface up here to the origin. That kind of looks like it makes sense, right? It's somewhere in this region here. This is going to be an x value of root 2, y value of root 2, and a z value of 1. And that gives us the closest distance to the origin. This method's really powerful because it allows us to work out fairly complicated problems. How do we maximize? How do we minimize something subject to constraints? And all we need to do is we need to look at the gradients of our function and then do a little bit of manipulation. Yeah.
Can you scroll up?
Yes.
So when we're minimizing, is
Yeah.
it always that, like for 3 dimensions and for any amount of dimensions, is it always just that root? Like
if you were minimizing distance, yeah, it would be that. Because we're talking about distance here and we're saying what's closest to that, then it would be, yeah, you can just use the square root thing. In fact, you can just use the squared version of it, and then that would still give you the minimum distance. Which point is the minimum distance? Of course, you might be asked to minimize other things. For example, if this was an economic problem, you might be asked to minimize the cost subject to various constraints, right? If you are minimizing, BC's health budget and you have to spend a certain amount on cancer care and a certain amount on infectious disease control and so on, you would have to minimize other things. So
we have to come up with that equation as well.
No, I would not put something into an exam other than I would either give you the explicit thing or I would say something like distance. Okay, it's going to be something that you would have met before that is quite obvious. Okay, that's a good question. Yeah. Any other questions? Okay, if not, you're free to go. Have a good weekend, everyone. Oh, quick announcement as well. I've got office hours now, but unfortunately I have to cancel office hours next week. So if you have any problems next week, do send me an email and I'll try to find a way to solve it otherwise. Okay.